A new study, published yesterday in the journal Nature Astronomy, reveals a type of devastating event, most often associated with films about disasters and the extinction of dinosaurs, possibly also contributed to the formation of the surface of the Moon. A group of international scientists led by the Royal Ontario Museum discovered that the formation of ancient rocks on the Moon could be directly related to the large-scale effects of meteorites. Scientists have conducted new research on a unique rock collected by NASA astronauts during the flight of Apollo 17 to the Moon in 1972. They found that it contains mineralogical evidence of its formation at incredibly high temperatures, above 2,300 degrees Celsius, which can only be achieved by melting the outer layer of the planet in the event of a strong impact. In the breed, researchers discovered the former presence of cubic zirconium, a mineral phase often used instead of diamond in jewelry. This phase will only form in rocks heated to temperatures above 2,300 degrees Celsius, and although it has since passed into a more stable phase, a mineral known as baddelite, the crystal retains the distinguishing features of a high-temperature structure. Studying the structure of the crystal, the researchers also measured the age of the grain, which shows that baddelite formed more than 4.3 billion years ago. It was concluded that the high-temperature phase of cubic zirconia should have formed before this time, suggesting that strong shocks were critical for the formation of new rocks on the early Moon. 50 years ago, when the first samples were returned from the surface of the Moon, scientists raised the question of how the rocks of the lunar crust were formed. Even today, the key question remains unanswered. How did the outer and inner layers of the Moon mix after its formation? This new study shows that violent shocks that occurred more than 4 billion years ago could lead to this confusion, creating a complex landscape of stones visible today on the surface of the Moon. Rocks on Earth are constantly being processed, but there are no plate tectonics or volcanism on the Moon, which allows us to preserve our older rocks, explains Dr. Lee White, a Hatch researcher at TROM. By studying the Moon, we can better understand the earliest history of our planet. If large overheated bellows created stones on the Moon, the same process probably happened here on Earth. When I first looked at this rock, I was amazed at how the minerals looked different compared to other Apollo 17 samples, says Dr. Arnold Chernock, ROM researcher and co-author of the study. Although it is a grain smaller than a millimeter in size, the baddelite grain that caught our attention was the largest that I've ever seen in Apollo samples. This small grain still contains evidence of the formation of a shock basin hundreds of kilometers in diameter. This is important because we do not see any evidence of these old influences on the Earth. Dr. James Darling, co-author of the study, says that the data completely changes the understanding of scientists' collected samples during the Apollo missions and in fact the geology of the Moon. These unimaginably strong impacts of meteorites help build the lunar crust, not just destroy it, he says.